Now that we've been introduced to the idea of limits at infinity, let's talk a little bit about those just using polynomial functions. Rational polynomials, which that just means polynomial on top, polynomial on bottom. So given this explicit function, 6x squared plus 2x plus 7, the first thing we want to do is find the limit as x goes to positive infinity of that function divided by x. So what we're really looking for is the limit as x goes to infinity of 6x squared plus 2x plus 7 over x. So in this case, what you would like to do, what you typically want to do is you want to find the the largest degree of polynomial. So in this particular case, the largest degree is 2. And then what you want to do is you want to factor out that largest degree. So in this case, x squared. You want to factor out x squared from every term. So using algebra here, what we will get is the limit as x approaches infinity of x squared. So what we'll have is 6 plus 2 over x plus 7 over x squared times 1 over x. So those are that's how we would factor that in that way. And the reason we want to do that, we always go by the largest one, is so what we see is we can erase, and that's really what we have is a 6 plus all these terms over x. And what we know is that the limit, whether you're going to positive or negative infinity, over 1 over x to a power, because if it's 1 over x squared, it's just 1 over x times 1 over x. So that's always going to be 0. So what you're going to find is every one of these pieces are going to go to 0. So you're going to get 0, 0, 0. So by doing that, then what you're going to have is positive infinity, because it's going to be 6 over 0, but it's not 0, right? It's going towards that's driving down towards 0. It's not directly 6 over 0. It's 6 over a really small number, so it's shooting off to positive infinity. And that's kind of how you analyze that. So using that technique, what you can do is you can do the same thing here with x squared. So in this case, we're still going to factor out x squared because x squared is the largest common, or it's the largest degree polynomial. So I'm going to say x squared 6 plus 2 over x plus 7 over x squared all over x squared with a 1. So again, the x squareds are going to cancel. And that's going to leave me with 6 because that term vanishes as we go to infinity, and all we're left is 6 over 1. So what we found was, in this case, the degree was larger on top, it shot off to infinity. The degree was larger, or no, the degree was the same size, it stayed finite. So if the degree is larger on bottom, I wonder what we expect. So in this case, x cubed is the largest piece, so let's go ahead and factor that out. So that's 6 over x plus 2 over x squared plus 7 over x cubed. Sorry, there's a limit as x goes to infinity here. So since these two are going to vanish, you're going to have 0, 0, 0 over 1. So that tells me my limit is 0. So when the degree was larger on top, it went to positive infinity here. When the degree was the same, it went to a finite number. When the degree was larger on bottom, it went to 0. So let's see if we can use that knowledge to analyze this function. So I have 6 plus this. Now, what I notice is that the degree of the polynomial is larger on bottom. So since the degree is larger on bottom, I'm going to expect this case. But let's rewrite it just to be safe. So we could rewrite that as 1 over x squared over 1 plus 1 over x to the fourth. And that's pretty ugly, but what we're going to see is that as the limit approaches infinity, that's going to disappear, and that's going to disappear. And that's going to happen even when we go to negative infinity, right? It's that one's going to disappear, and that one's going to disappear. So it's going to be 0 over 1. So that tells me that long term, that piece disappears, and you're only left with the 6. So long term, we know that we're only left with 6, but then we have to figure out a little more to actually graph this thing. So one of the things you can do is to find the y-intercept. So you just plug in 0 and see what happens. If I plug in 0, I get 0 over 0 plus 1, so that also vanishes. That tells me that it's at 6 at 0. Then what I would need to do is I would need to apply the first derivative. And what you're going to find with the first derivative is you're going to have a critical point, and I don't remember exactly where it is, but you're going to have a critical point, and it's going to be a minimum. So since you know it's going to be a minimum, you're going to have this type of behavior, but you know that the long-term behavior, it comes back up to 6. So you get that, and you get it. And we get this behavior because it's an even function. And we know it's an even function because if we plug in a negative value, we get the same function as a positive value, right? So if I plug in negative x, I get 6 plus negative x squared over negative x to the fourth plus 1, which is 6 plus x squared. So I get the same function for negative value, or I get the same function outputs for negative values as I do for positive values. So as a result, I really only need to graph this side, and then I can reflect it over to get what this graph looks like.